Okay, so I'm starting to cut back on what I'm writing about the old derivative review stuff, so I just want to get the real meat of our basic facts. So the derivative of constant is 0. Derivative of x to the power a, bring the a down, x to the a minus 1. The derivative of arctangent is 1 over 1 plus x squared. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant is secant times tangent. The product rule, if I have the derivative of two functions, f times g, I take the derivative of f times g plus f times the derivative of g. The chain rule, if I have a function g inside a function f, the derivative of this is f prime of g of x times g prime of x. So in other words, you take the derivative of the outside function, leave the inside pristine, untouched, and then you times by the derivative of the inside function on the end. Okay, so these are the important rules for derivatives. And pretty much if you know these rules for derivatives, you're in good shape as far as our class goes. You will be adding a little bit to this list next quarter in that you'll have some more functions that you'll add over here. But these are the two basic rules to remember. Now, this is not what we talked about last time, but we spent a lot of time doing this last time, so I thought we might as well throw it back up on the board. Related rates. These are one of the two things that we can do for a word problem. So you can bet there's definitely going to be a word problem on the next test because, well, we have all these fun things. One of them is related rates, and one of them is optimization, which we'll talk about in a few lectures. So what's this? Well, you're given some rate or possibly rates, more than one, and you want to find another related rate. So we have some things which are related to one another, and as one thing changes, something else related to it changes. For example, we might have a balloon, and we're blowing up the balloon. And we can say, well, I'm putting so much air into the balloon at every second. And I can ask, well, how big is the diameter increasing of this balloon? Well, the diameter is related to the volume, so when I change the volume by blowing air in, of course, it makes sense that I should be changing the diameter. And if I know how fast the volume is changing, I should know how fast the diameter is changing. So these rates should obviously be related, and it's how do we figure out what the relationship is? Well, the first step, which is always the hardest step, is to set up the relationship. And probably the thing that makes this really hard is we have to translate these word problems into our fun calculus language. So we have to strip away all the stuff that's not important. So I was telling a story last time about how you were doing calculus problems late at night, you were driving home, your wife was there waiting for you, just ready to talk to you about you staying late doing calculus. Those things aren't important. You have to remember to strip away. Late at night is not important. You're driving home, not important. You have to think, okay, what's important? You say, okay, well, what is it I'm trying to relate? The things you're trying to relate, you call those some variables. X, Y, Z, theta, whatever you like, whatever's convenient. There's no right or wrong answer. Well, there's wrong answer if you get the wrong answer at the end, but naming the variables, there's no right or wrong answer as to how you name them, as long as you name them and be consistent with them. And then you look for relationships, and there's just a few basic things you have, like similar triangles, Pythagorean theorem, things like sine, cosine, tangent, the area formula, volume formulas, things like that, all very simple stuff. I do expect you to know things like the area of a circle, the area of a square, the volume of a cube, surface area of a cube. But if I ask you something like the volume of a cone, I would give you the volume of a cone. I'd give you the equation. I don't expect you to remember that off the top of your head, because that's not one a lot of people memorize. Okay, so setting up the relationship, naming our variables, finding a relationship. This is almost always the hardest step. Because once you have this, the rest is really straightforward. You take the derivative with respect to t. And the reason we're taking the derivative is we're looking for the rates. Rates is one of those key words that you sort of know right away. Okay, if I see the word rate, there's something with the derivative going on. The relationship doesn't have anything to do with the derivative. For instance, the volume of a sphere, if we go back to the balloon. We can relate volume to the diameter, but that doesn't say anything about how the rates are related. It just says how the volume and diameter are related. So by taking the derivative, now I have a relationship that also involves the rates of change. So that's why we do step 2, to get to these rates. And then step 3, well, we take the information that we have, and we should have everything that we want except for the desired rate. And so we solve for it. And we're done. Woohoo! Okay. So that's related rates. Now, what we really talked about last time, and we only got into it a little bit, but we did most of it anyways, is we're starting Chapter 4. Chapter 4 is the applications of derivatives. in the beginning of Chapter 4 is Section 4.1, and the moral of the story is that tangent lines are good. Approximations to the function near the point of tangency. That's the key thing to remember. If you remember back to the very first day of class, we drew this picture and we said, okay, if you blow it up, the function, you keep blowing it up over and over and over again, eventually it looks like a line. And in fact, that line is the tangent line. And the idea is, by blowing it up over and over again, we're looking closer and closer. We're looking near the point of tangency. And so if I were to look really close, so here I draw a function, y equals f of x. I drew in the tangent line here at the point A. Close by, you can barely distinguish the function from the tangent line. Of course, the further away we get, the worse that the tangent line becomes as an approximation. So the basic formula, if you remember for derivatives, was that we had f prime of a is our limit as, let's say, x approaches a, f of x minus f of a over x minus a. Where, what is fx minus fa? Well, this is really the change in the function, so we call it delta f, a change in the function f. What is x minus a? It's the change in your x-coordinate, delta x. So in the picture here, delta f is how much our function changed. So if here's a, here is my x. So my delta x is how much I go along in the x-axis. My delta f is how much I change from the original value of the function, which is here, to the current value of the function, which is here. So that was my change in my function. And the moral of the story is that for when x is close to a, this delta x is small. This ratio delta f over delta x is roughly f prime of a, which is what I wrote here in a slightly different format. The change in f is approximately the derivative times the change in x. So in other words, when delta x is small, if this is my change in my function, and here's my change f prime of a delta x, which is really just how much my derivative, how much it changes according to the tangent line, these two changes are good approximations for one another. So what's one of the things we talked about we can use this for? Well, one of the things we talked about with this function is we might want to talk about how much, if we say have some construction process where you have several steps. And in construction, you have this sort of ideal size. But realistically, you always are going to have a little bit of error. Maybe you want to make something 12 inches wide, but you're not going to get exactly 12 inches. It'll be 12 inches within, say, a quarter of an inch. And you say, well, okay, what does that quarter of an inch error change? Well, that quarter of an inch error is essentially saying this delta x is within 1/4 of an inch. And you say, well, I figured out what the derivative is. I know what this is. It's within plus or minus 1/4 of an inch. And so it gives me sort of a range for how much my function can vary from what I truly want it to be. We did an example last time about this where we were talking about a pizza. And, of course, ideally your pizza is exactly circular, but maybe it's exactly a circle of, say, 18 inches, but we might be off by a little bit. How much does that affect the surface area of the pizza, the good part of the pizza? And we went through and said, well, if we know how much we're off, we can get a good estimate for how much our function changes. So another thing is, the book talks about, is the linearization. Let's see, what does it call it? There's a few different names depending upon what book you read. Oh. All right, well, I'm going to call it local linearization. I think the book just calls it linearization. And we essentially did an example of this last time, too. I just didn't call it that. And you might think, okay, so linearization, we have this whole new idea. Well, what's the basic thing it's trying to do is it's trying to say you have a function. Locally, it looks like a line. It looks like a linear function. So when I say a linear function, essentially I mean a function of the form mx plus b, a line. You can tell I mean a line because, in fact, here's a clue. See, the word line is inside of here. So when I talk about local linearization, I'm talking about something that looks like a line nearby. And in other words, if I think about the function, if I were to zoom in, as we've done before, and look at the function here, locally it looks like a line, and I want to find what that line is, and I'm going to call that the linearization. And the idea being that the function is roughly following this line. Now, what line do we take? Yeah, you take the tangent line, right? This is one of the things we started from day one. We want to find the best line, so the local linearization is really just saying the tangent line. So in other words, it's the function that's the tangent line. So there's nothing new. So local linearization, we usually call this L of x. And so we just put in the tangent line on the other side, and we already found an equation for the tangent line. It's f of a plus f prime of a times x minus a. So if you just go back and remember, if you might remember as y minus f of a equals f prime of a times x minus a, but I just put everything on one side, so I have y equals. And the moral of the story is that the local linearization is approximately f of x for x near a. And that's just the same thing as saying that the tangent line is approximately f of x for x near a. So how did we use this last time? Well, we said, I want to estimate square root of 26. And then I said, well, OK, so what we'll really do is we'll estimate square root of 26 minus square root of 25. So in other words, we'll get a handle on this, and then we'll figure out what the square root of 26 should approximately be. Really what we are doing is thinking about this idea of local linearization. So here I say square root of 26. Well, if I think of my function f of x as square root of x, and I say, OK, square root of 26, what's near square root of 26 that we know? Well, 25, because the square root of 25 is 5. So in that case, we went through and we saw, OK, we had the square root of 25 plus the derivative at 25, which I went through it again, is this, times x minus 25. So the local linearization is essentially this. We did this last time. I'll do another one in just a second here. So that L of 26 is the square root of 25 is 5. 1 over 2 times square root of 25 is a tenth. And 26 minus 25, which is 5.1. And we said, well, the local linearization is approximately what the function is. So that's approximately square root of 26. So 5.1 is approximately root 26. And we even said, I think it turned out to be something like 5.099 or something like that. So if you have your calculators, you can test it yourself. You'll see it's a pretty good approximation, better than 5. And depending on how far you go in your calculus classes, you'll find ways to get better and better approximations. So this local linearization is actually sort of a preview, a hint of things to come. And there's something which are called Taylor polynomials and Taylor series. The idea being, well, suppose I don't want to find the line. Suppose I want to find the quadratic, a second-degree polynomial, which really mimics the function. It's essentially going to be the same thing, but your next term is going to involve a second derivative. So you'll learn about that depending on how far you go on in your calculus course, but we won't be learning about that here. OK, so local linearizations are great for helping us approximate the functions. There are, of course, some caveats. This is an approximation. It's not going to be exact. As we saw last time, we already know that 5.1 is going to be too high, because if I think about square root of 26, I use 25 here. Whoops, let me look at 25. I use a tangent line at 25, which will do something like that. So if I look at 26, the tangent line is giving me something which is too high. And then the problem is, well, OK, how good of an approximation is it? Well, it depends on a couple of things. One of it depends upon how nice your curve behaves. So for instance, if the curve, if you have your tangent line at a point, and your curve is fairly shallow and not changing very much, not a bad approximation. So here, tangent line is OK. Or I'll say tangent line good. But you could also have a similar tangent line, but then have your curve do something like this. And here, tangent line is not good. Or I'll say mediocre. I don't want to say bad. Not as good as it could be. It's not being all it can be. And so this is just something the book points out. This is not important. Don't worry about this. This is just some intuition. So what's the difference between these two pictures if I think about these as functions? Well, if I think about this as a function, what do you notice about this? Well, if I think of the second derivative is changing in both cases. In fact, you can show the second derivative is negative. What's the difference in terms of the second derivative? Well, here the slopes are changing very slowly. So this has a small second derivative. So when I have a small second derivative, the slopes are changing very slowly, and so the tangent lines won't change very much. And they make pretty good approximations nearby. Here, what's the second derivative? Well, it's changing very, very rapidly. So here, where the tangent lines aren't as good is where you have a large second derivative. And so, again, you might say, well, OK, so how can I use information about the second derivative to get a better approximation? And again, that's Taylor polynomials, which we'll do later in the future. So let's do one quick linearization, and then we'll start the next section. Actually, let's do it over here. So find the linearization of y equals arctangent x at x equals pi force. Oh, no, sorry. 1. OK. 1. Yeah, that's a nice number. OK, find the linearization of y equals arctangent x at x equals 1. So what do we do? Well, we find the tangent line. So essentially, in other words, it's saying this arctangent of x, that's our f of x here. And this x equals 1, and this is really saying that a equals 1 is the way you can think of it if you like. When I'm specifying a point, that's really where my a is. All right. So what do I need? Well, my linearization is going to be my function at my point plus the derivative evaluated at the point times x minus a. So I'm just rewriting what I wrote down over there. There's nothing different. So let's plug in what we know. This is arctangent of 1, because the function is arctangent, a is 1. Now, what's the derivative of arctangent? Yeah, 1 over 1 plus x squared. Lo and behold, fortunately for us, we have it written down here. So now I'm going to plug 1 into there. So 1 over 1 plus 1 squared. So that's my f prime of a, x minus pi force. Sorry, x minus 1. You'll see why I keep writing pi force here in a second. What's the arctangent of 1? It's pi force. See, that's why I kept wanting to write pi force, because I knew the pi force was coming up, but I was just so excited to see pi. I was jumping the gun. It happens to me all the time, because pi is such a cool number. You can do so much with it. OK, but that's why I kept writing pi force. The arctangent of 1 is pi force. Now, a different way of thinking about it, if you don't remember it, to find the arctangent of 1 is the same question as saying, what angle, when I take the tangent of it, gives me 1? So tangent of what angle is 1? Pi force. Tangent of pi force is 1. That's why arctangent of 1 is pi force. 1 over 1 plus 1 squared is plus a half times x minus 1. And we can leave our answer like this. So that says if I want to approximate the arctangent function near x equals 1, I can use this equation here. So if I want to find, say, arctangent of 1.01, I would plug it in and just get a number here. Because we get pi's in there, I don't want to muddy the waters. All right. So here we saw derivatives are great because tangent lines are great. Let's look at another reason why derivatives are great. So section 4.2, or section the next, if you like, we're starting to look at doing extreme values. Yeah, that's right. Extreme! Ah! Yeah, exactly. So what do I mean by extreme values? Well, in other words, we're looking for what we call maximums and minimums. Okay, that's when we talk about extreme values. We want to find the largest and the smallest. Now here, we're actually going to have two kinds of maximums and minimums. And let me quickly write these down. So there's first off what we call a global max. So I should say we're going to have a function. Let me write this down over here. OK, so for some f of x, on some, usually we do an interval. So by an interval, I think it means something like from 1 to 5, or we could go from 0 to infinity, or from -8 to 3, just some range of values for x. So a global max is a point A where f of A is bigger than or equal to f of x for all x in the interval. I'm writing this really long here. I'm going to shortcut in the next step. Okay, so global max is exactly what you think it is. To be a maximum means you're bigger than or equal to everything else that you could be. So that's the first thing we say here. The function at A is bigger than or equal to the function at any other point that I'm considering. So we have this interval. So we're restricting our function to some set of interval, some range of values. So we may have a function defined on all x, but I'm just looking at these set of x here. Okay, so the max means it's bigger than or equal to everything. The global, so max means it's bigger. Global means it's bigger for everything. Well, there's also a global min, which is a point A where f of A is less than or equal to f of x for all x in the interval. Same idea. What does it mean to be a minimum? Means you're less than or equal to anything else. And because it's global, means it's anything else that we could consider for our function. So for all x that we're considering. Now this is one type of, this is one type of max and min. There's another type of max and min, which are called local. So a local max is a point A where f of A is greater than or equal to f of x. But now let's think about the difference in our word here. Global, we said, for all x that we might encounter in the interval. What do you think local should mean? Yeah, so one of the words I heard was for all x nearby A. So nearby is the right intuition. So in other words, if I look at some small area right around the A value, not all possible x values, just the ones near A, then it's bigger than everything in that small region. I don't care what happens far away. Just near A, it's bigger than or equal to everything. And then a local min, well, no surprise, is a point A where f of A is less than or equal to f of x for all x nearby A. Okay. So I'm not going to write everything out, just because if I did, we'd take half a class to do that. But the intuition is, what do you mean by max and min, and what do you mean by global and local? Max is bigger than everything, min is smaller than everything, global is for all points, local is for points nearby. Okay? Now, we're going to be focusing on this lecture mainly on the globals, the global max and the global min. My goal is to find these. Eventually, in the future lectures, we'll also talk about how to find these as well, local max and local min. Okay, let me just draw a picture here. All right. Just so we can build up some of our pictures here. Okay, these are all memorized by now, no problem. So, I should use black for a function. So here's our picture. We have some interval, A to B, and I have some function. I'm going to start here, going to go down. Oh, let me make this a little bit more explicit here. Okay, and whoop. Okay, so suppose this is our function here. let's see if we can figure out what we can say about points. So for instance, what can we say about this point here? Yeah, it's a local min. So if I look at that point, I'll just use LM for local min. If we look at that point, clearly any point nearby is smaller than it. The value of the function is, the value of the function is smallest for the local min nearby that point. Now, is this the global min? No, because I can have points over here which is smaller than this. So, okay, it's not the global min. So where is the global min? Well, if you look at it, it's right here on the end. In this case, if my function went from A to B, it's at the endpoint B. Now, of course, the one thing to point out, which is obvious, if it's a global min, it's also a local min. So really, one of the steps we're going to do in finding the global min and global max is we're going to find out where the local mins and maxes should be, because the global min is also a local min and also similarly for a global max. Okay, what about this point? This is a local max, but it's not a global max because over here I can get higher. In fact, the global max is way up here. This is a global min, and of course it's also, whoops, I shouldn't say equals, comma, local min. You know, I just noticed that min and max start with the same letter. This is probably not the best thing. Okay, how about LMA? LMI. There we go. GMI. I thought I was being so sophisticated, and then I realized it was really stupid. All right. That happens often. And, of course, we have other points. So, for example, here we have, this is a local minimum. Here we have a local maximum. And because I made my life hard, I put a little wiggle in here. There's a local min, and there's a local max. Okay. So here's an example of a function. And we've marked the local mins, local max. It's easy when you see the function to really pick things out. It's kind of clear. Now, when you can't see the function, you can't plot it, you have to work a little bit harder to get it done. Now, here's a question. We're looking for our global mins and our global maxes. Do they always exist? Well, the answer is no. So, for instance, suppose I look at the function f of x is 1 over x on the interval from 0 to infinity. What does that function look like? Well, it looks suspiciously like this. Now, what's the maximum? Well, there is no maximum because it grows unboundedly. It can get arbitrarily large. Okay, so there's no max. What's the minimum? Well, we say intuitively it's 0. But we have to be careful here when we're talking about global max and global min. We're talking about there's a point A where I plug it into my function. And that's going to be the smallest value. Now, this can get smaller and smaller. So we know it's bounded below by 0. And I get arbitrarily close to 0. But can I ever get exactly to 0? No. No matter what A I plug in, it's not going to be the... Now, if I plug in an A here, say this is A, well, clearly that's not the minimum because I just go further to the right. And I get smaller. So there's no minimum. So we have to be careful. We have to say, OK, we want to restrict it to functions where we know there's going to be a min and max. And it turns out we're in luck. There's a nice fact. And we're not going to prove it because it takes a lot of work to prove it. We'll just assume it. Here's a nice fact. A continuous function on an interval a less than or equal to x less than or equal to b. So if you look in the book will call this a closed interval. The idea being that we include the endpoints. Now here, what was our problem? 1 over x is continuous. That's not a problem. But we weren't including endpoints. So what if we have a continuous function on an interval where we include endpoints, it always has a global min and a global max. And the good news for us is this is the ones we'll always be considering when we're looking for the global min, global max. We'll always be focusing on this case. or it'll be clear about what happens as we go to infinity, something like that. All right? So here, notice my function is continuous. The way I drew it, it's a continuous function, and I included the endpoints. Therefore, I knew I would have a global min and a global max, and we were very easy to find it. All right. Well, so far, most of what we've talked about is definitions. Now we need to start thinking about, OK, how do we find these points? So let's come back to our picture here. We think about, OK, what do the points where there's local mins and local maxes, what do they have that points that we haven't circled have? So for instance, I didn't circle this point over here. Now, how do we know that's not going to be a local min or a local max? I mean, just looking at the picture, I can see it's not a local min or a local max because I can see it's going down. But picture-wise, as someone said, if I think about the tangent line, because the tangent line, remember, really is mimicking the function nearby. So the tangent line is going down. So the point here, OK, this is not the best picture because it looks my lines are straight up and down. But the point here is if the derivative is not 0, I can't be at a max or a min. Why not? Well, because, oh boy, OK, we'll erase you. If I have my function, and here's my a, I know the derivative is not 0. So that says my tangent line is not flat. So my tangent line looks like this. So if this is my tangent line, and I think about my function, what I remember is that my function, from the linearization, f of x is really approximately f of a plus f prime of a times x minus a. And this is a good approximation for x near a. So if my derivative is positive, then if I go a little bit up, what happens? Well, I have f of a plus f prime of a is positive, and x minus a is positive. So in other words, I'm looking over here, which says that on here, f of x, on this side, f of x is bigger than f of a for x near a. Similarly, if I go in this direction, the x minus a is negative. So this whole term is negative. It's a positive times negative. And it tells me that over here to the left of a, f of x is less than f of a. OK, so what do we have? We have the following. If f prime of c, or I'll say a, is greater than 0, and similar argument, f prime of a is less than 0, then not min or max. Oh, good. We fit it in the box. So if the derivative is positive, it's not going to be at a min or a max, because I just move either to the left or to the right, and I'm going to go up and down. If the derivative is negative, it's not going to be a min or a max, because I can either move to the left or to the right. My function will go up or down, because I know what's happening with the tangent lines, and that's telling me what's happening with the function. OK, so now I know to rule out these points. OK, so what points are left? Yeah, there's not a lot left. Because I basically say wherever the derivative is positive, I'm not going to look at those points. Wherever the derivative is negative, I'm not going to look at those points. There's no, how many options are left to us? Well, not very many. Therefore, if we're at a critical point, if we are at a max or min, then either the derivative f prime of a, let me make that look like an a. Either the derivative is 0. Now, I use the word either, so that means there's 2. So the derivative is 0. OK, so we have derivative is 0, derivative is negative, derivative is positive. What other option do we have? Yeah, there is no derivative. F prime of a does not exist. OK? This is our key fact. It shows us why derivatives are useful for hunting for global maxes and global mins. Because I can look for f where the derivative is 0 or the derivative does not exist. Now, in case you forgot an example where the derivative does not exist, it's the absolute value of x. Now, let's suppose I'm trying to find the max and min of this function, say from -2 to 5. Now we can just look at the picture and say, well, okay, the max is over here, which is going to be 5. Where's the min at? No, it's going to be at 0. Now, we talked about if we are on a max or min, then either derivative is 0 or derivative is undefined. Here I want to be a little bit careful because we have these endpoints. Don't worry about those. I will talk about those in a second. You can think of it as saying, well, I can't really take the derivative because I can't talk about what happens to the right. If I'm only going from -2 to 5, I can't go from the right. If you want, you can think of it sort of as being the does not exist case. Now, 0, what's the derivative of the absolute value function at 0? We talked about this before. Give you a hint. Does not exist. Does not exist. That's right. Because when I came in from the right-hand side, I'm thinking, oh, the derivative should be 1. When I came in from the left-hand side, I was thinking, oh, the derivative should be -1. And -1 and 1 don't match up. So we did it by looking at two one-sided limits. So it is possible for the derivative to not exist. All right. Now, we do give these a name. These are called critical points. So that's where points where the function has the derivative of 0 or where the derivative is undefined. Okay. So let's do some practice here. So suppose I give you a function. F of x is x cubed minus 9x squared plus 24x plus 1,000,000. And I ask, where are the critical points? So if I give you a function, in this case, x cubed minus 9x squared plus 24x plus 1,000,000, and I ask where are the critical points, what's the first step? Take the derivative. Because the critical points have to do with the derivative. We look for where the derivative is 0 or where it's undefined. OK, so we take the derivative. What's the derivative of x cubed? 3x squared, derivative of 9x squared, 18x, derivative of 24x, 24. And, of course, the derivative of 1,000,000, 0, which is why it's not important what number I put here. I could have put any number here. That number doesn't affect where the critical points are. OK, so now I look for where it's undefined or does not exist. Well, it's a quadratic. It always exists. So in this case, I don't have the does not exist option. And most of the time when you talk about critical points is you have the derivative is 0. So let's figure out when does this equal 0. So when does 3x squared minus 18x plus 24 equal 0? But what can we do to help solve this? Yeah, first thing we can factor, let's divide everything by 3. So 3x squared divided by 3 is x squared. 18x divided by 3 is 6x. And 24 divided by 3 is 8. So it's the same as solving x squared minus 6x plus 8 equals 0. Because can we factor this? And the answer is yes, we can if we're good enough. If not, we throw it into the quadratic formula. So I'm looking for two numbers that multiply to 8 but add to 6. Yeah, 2 and 4. So x minus 2, x minus 4. And the really cool part about this is if I have two things multiplying together and they equal 0, one of them has to equal 0. So this tells me that one option is x equals 2, and the other option is x equals 4. So here are the critical points. They're going to be at 2 and 4. And the points 2 and 4 will be important points for our function. OK. We can do some other examples. Now, there is a word of warning. So here we made a statement that if we are at a max or min, then either the derivative is 0 or the derivative does not exist. The opposite does not have to be true. In other words, it doesn't have to be true that if the derivative is 0 or that the derivative does not exist, I'm at a max or min. Let me give you an example of that. classic example. Suppose my function is f of x equals x cubed. Let's find the critical points, and then we'll plot it. So find the critical points, I look at the derivative, because the derivative tells me everything I want to know about critical points. In this case, root of x cubed is 3x squared. And then I set this equal to 0. So for what values of x does 3x squared equal 0? 0. Yeah. X equals 0 is the only critical point. So we do have a critical point. But is it at a local max or a local min? Well, what does the function of x cubed look like? It looks like this. It comes up, and then it goes flat, but it doesn't go back down. What it does is it starts going up again. So it's true that I actually have a horizontal tangent line at x equals 0, but it's neither a local max or a local min. So be careful. The converse, as we would call it, is not true. So this tells us where to look, but it doesn't guarantee. If the derivative is 0, I'm not guaranteed that I have a local max or a local min. OK. So now let's talk about how do we actually go about finding these global maxes and global mins. Well, we have a pretty good idea of where they can happen. So what we're going to do is we're essentially going to say, we know where it should happen, and we're going to make a list. We're going to say, it's going to happen at one of these points. So let me catch up to what I was saying. Finding a global max / min. OK. So the first step is we're going to make a list of candidates. So in other words, we think we know where it's going to happen. There's only a couple places that it can happen. So we're going to make a list of candidates for it. What is going to make our list? Well, endpoints will always make the list. So we're talking about finding a global maximum, and we're talking about on some interval. A less than or equal to x, less than or equal to b. So the endpoints. In other words, the a, comma, and the b. This is not a point. Let me make clear it's not a point. A and b. X equals a, x equals b. OK, there we go. Now it's very clear it's not a point. All right. So the endpoints will always be in there. And then the other ones come from the critical points. So these are and there's essentially two kinds of critical points to look for. And you look for them simultaneously. The derivative is undefined, and the derivative is 0. OK. Now anything I should be able to spell derivative. OK. I should know by now how to spell derivative. All right. So either the derivative is undefined or derivative is 0. Anything that's not on our list ain't going to be a local max, local min, and it ain't going to be a global max, global min. Excuse my bad English. It just is not going to happen. So all the points that we're interested in, if we're hunting for global max and global mins, are these points. And these will be just a handful of points. All right. So here are where they should happen. So what's our next step? Well, this tells us where we should happen, but now we have to have something to compare as far as global max, global min. So what we do is we plug all these points into the function. So when I talk about the points that we just made in step 1. So now we have our list of points, and now we have our list of our values of our function. And we're looking for the global max and the global min. So how do we find the global max on this list? Well, we just find the largest one. So the largest value is a global max. How do you find the global min? Yeah, it's the smallest value. So let's go through and see if we can do one really quickly. All right. Suppose I ask you to find the global max and min and I give you a function. In this case, my function is 2x cubed minus 15x squared plus 24x plus 7. And then the interval is 0 less than or equal to x less than or equal to 6. So I give you a function, and I give you an interval. So we know right away that we're going to have a global max or min, because this is a nice function. It's a continuous function. Polynomials are always continuous. And we have an interval where we have the endpoint. So we have a closed interval. So automatically we know there will be an answer. All right. So let's start making a list of points. I'll make my list of points over here. So here's my x values. Here's my f of x values. Now, what points automatically do we throw in? 0 and 6, because we always include the endpoints. OK, so 0 and 6. So I'm making a list of x values where the mins and maxes will occur. Now, I finished that. That's the endpoints. I also need to check for critical points. So the next step is take the derivative. And we look at it. 6x squared minus 30x plus 24. OK. Clearly, it's always defined. So we don't need to worry about the does not exist case. You always should just double check, but in this case, we have no problems. So now we look at it set equal to 0. We need to solve. Well, in this case, what can we do? Yeah, we can divide by 6. Everything has a factor of 6. X squared minus 5x plus 6 equals 0. Now, there are two numbers that multiply together to give us 6 and add together to give us 5. OK, good. Thank you. So there are two numbers that multiply together to give us 4 and add together to give us 5. 1, x minus 1, x minus 4. OK. So what other points do we add to our list? 1 and 4. And now we plug them into our function. Well, some of these are pretty easy. 0 is easy to plug in, because you get 0, 0, 0, and 7. OK, so got 7. 1 is not too hard. You get 2 minus 15 plus 24 plus 7. OK, well, 31, 33, 33 minus 15 is 18. All right. 4 we could probably do. 4 cubed is 64, so that's 128 minus 60, 68. Plus 7, 75, plus 96 would make it what? OK, obviously my math is bad. OK. All right. Well, never mind. I went way off. We'll say it's negative. Oh, wait. Sorry. We'll say it's negative 9. That's what the book told me. Oh, I'm way off. Oh, all right. Because 4. Oh, right. This. 4 squared is 16. So 16 times 15 is, what is it, 240. Yeah. OK, negative 9. And then 6, I won't even try to do that one because I'm going to mess it up. OK, 43. Positive 43. OK, so now we have our list. We found our points. We plugged them in. And now we look at it and say, OK, what's the largest number here? 43. So we say, OK, here we go. Here's our global max. What's the smallest? Negative 9. Here's our global min. So now we found our global max and our global min. Now, I haven't said anything about what is 0. Is it a max or a min? What is 1? Is it a max or a min? We haven't gotten to that point yet. That's what we will do next time. All right, so have a good day. I will see you on Wednesday.